Good morning, student. I am Professor Farin Sheikh from the Department of Chemistry, Tulsaram Chaturchand College, Baramati. Today we are going to learn FTIR spectroscopy under the Skill Development course 2021-22. So let us start. These are some contents which we are going to discuss in this lecture. The first is principle of IR spectroscopy. Atoms in any molecule and molecule as a whole is never stationary. They continuously rotate, vibrate, and also move from one point to another point, even at 0 degree Kelvin. When kinetic energy of entire molecule is zero, atomic nuclei vibrates about the bond which connects them. Atoms in the molecule can vibrate in number of phases. Each vibration requires definite amount of energy, that is vibrational energy level. If molecule is exposed to IR radiation, the molecule absorbs the energy of IR radiation, and as a result it gets excited to higher vibration energy level. The type of IR wavelength absorbed by molecule depends on the type of the atom and chemical bond in the molecule. When these absorptions are recorded, we get the IR spectrum. The IR spectrum consists of number of peaks. Each peak is due to particular vibrational excitation of a molecule. The position of absorption peak can be specified in terms of frequency or wavelength or wave number of the IR radiation absorbed. Frequency expressed in Hertz and wavelength expressed in mu. Types of molecular vibrations. The number of different ways in which a molecule can vibrate are known as fundamental modes of vibration. The number depends on the total number of atoms present in the molecule and geometry of a molecule. There are two main types of vibrations in the molecule: stretching vibrations and bending vibrations. Here you can see the types of molecular vibration. Stretching vibrations are divided into two types: symmetrical stretching and unsymmetrical stretching. Bending vibrations are also have two types: in the plane bending vibration and out of the plane bending vibration. In plane bending has divided into two modes: scissor and rocking. Out of the plane bending vibrations divided into two modes: wagging and twisting. Okay, so let us see how this scissoring, rocking, wagging or twisting happenings in actually. Okay, here you can see symmetrical stretching is divided into two types: symmetrical stretching and anti-symmetrical stretching or unsymmetrical stretching. Then bending vibrations: scissoring, rocking, wagging and twisting. Okay, you can see here in symmetrical stretching both bonds are stretching at the same time. In unsymmetrical or anti-symmetrical stretching, one bond is stretching and one bond get contract. In scissoring happens like a scissor. Both bonds are moving like motion of a scissor. In rocking, in case of rocking, both bonds go at left and right at one and the same time. In wagging, as we know that wagging and twistings are out of the plane bending vibrations, so they are two bonds in wagging come out of the plane and then go again in the plane at the same time, and in twisting one bond come out of the plane and another bond is in the plane, and then that in this way they are showing vibrations. Okay, hope you will understand this. Okay, so next is depending upon the geometry of molecule, the fundamental modes of vibrations are calculated as follow. Okay, depending upon the geometry of a molecule and the number of atoms present in a molecule, we can actually calculate how many fundamental modes of vibrations a molecule can show. Okay, for linear molecule containing n atoms, there are 3n-5 possible fundamental modes of vibrations, and for non-linear molecule containing n atom, there are 3n-6 possible fundamental modes of vibration. It means when a molecule have a linear geometry, then we will use 3n-5 we use these equation and we get the fundamental modes of vibration for linear molecule, and for non-linear molecule we will use the equation 3n minus 6, and after putting the value we get the fundamental modes of vibration for non-linear molecule. I have given here an example. First example is calculate number of fundamental modes of vibration for CO2. Solution: for CO2 n is equal to 3. How? As we know that there is in CO2 one carbon atom and two oxygen atoms are present, therefore n number of atom is equal to 3, and geometry of molecule is linear, therefore we will use formula 3n minus 5. By putting values in equation we get 3 into 3 minus 5, which is equal to 4. Therefore CO2 have 4 fundamental modes of vibrations. Okay. Now we will discuss our today's main topic, which is FTIR. We will discuss about IR till we will discussing about IR. Now we will start FTIR. So what is FTIR? FTIR stands for Fourier Transform Infrared Spectrometer. FTIR is a instrument. Okay. Fourier transform is a mathematical operation which can separate the individual absorption frequencies required for the interferogram. Interferogram is the signal that is received by computer in FTIR and produce a spectrum virtually identical to that obtained with the dispersal spectrometer. These types of instrument is known as FTIR. Okay. Here is the instrumentation of FTIR. You can see FTIR consists of a mirror, two mirror, one is fixed mirror and next is moving mirror, then both and beam splitter, infrared source, sample cell, detector, computer, FT transform and printer, which gives us IR spectrum. Okay, so let us discuss this instrumentation. FTIR uses an interferogram to process the energy sent to the sample. In the interferogram, the source energy passed through a beam splitter and mirror placed at 45-degree angle to the incoming radiation, which allows the incoming radiation to pass through but separate it into two perpendicular beams. One beam is undeflected and other is oriented at 90-degree angle. One beam which is oriented at 90 degree as in the given diagram goes to stationary or fixed mirror and return to the beam splitter. The undeflected beam goes to a moving mirror and also return to the beam splitter because of the motion of the moving mirror. The path length of the second beam transfers to the vary. When beams meet at the beam splitter they combine, but due to difference in wavelength causes the constructive and destructive interferences. Okay. In this instrumentation you can see here a mirror is placed as a 45-degree angle to the incoming radiation. Here is the infrared source. To that fixed mirror is placed at the 45-degree angle. Okay. And as I have told you, one undeflected, the other oriented at 90-degree angle. One beam oriented at 90 degree as given in the diagram goes to stationary or fixed mirror and return to the beam splitter. Okay, one beam is going to the fixed mirror and deflected beam going to the moving mirror, and also it returns to the beam splitter. The motion of the mirror, this motion of this mirror is because of the motion of this mirror causes the path length that the second beam transfers to vary. Okay, then these beams or rays of light are will get reached to sample cell, to the detector, and finally to the computer. Okay, next, the combined beam containing these interference patterns are called as interferogram. Before reaching the computer, you can see there we have mentioned in the diagram interferogram. Okay, in between detector and computer there is interferogram, which the signal of the which what we have called to the interferogram is the signal the computer receives. Okay, interferogram contains all the radioactive energy coming from the source and has a wide range of wavelength. The interferogram generated by combining two beams is oriented towards a sample by the beam splitter. The modified interferogram signal that reaches the detector contains information about the amount of energy that was absorbed by at and every wavelength or frequency. Means interferogram consists of information about how much amount of energy a molecule or atom absorb at each and every frequency or wavelength. The computer compares the modified interferogram to the interference laser beam to have a standard of comparison. The final interferogram consists of all the information in one time domain signal that cannot be read by humans. Okay, interferogram contains information in one time domain signal, means in a signal or in a type of symbol which we cannot read, which a human cannot read. So how we can get that information or extract that information? So we need a FT means Fourier transfer. FT, which is a mathematical process, must be implemented by computer to extract the individual frequencies that were absorbed and to reconstruct and plot what we recognize as a typical IR spectrum. So interferogram gives us the information about the absorbed radiation, but we cannot read it. So FT helps us to convert it in a readable form or to understandable form. To obtain a spectrum of a compound, the chemist first obtains an interferogram of a background which consists of higher active atmospheric gases like carbon dioxide, water vapors. The interferogram is subjected to FT, which gives spectrum of background. Then chemists place the sample to be analyzed into the beam and obtain a spectrum resulting from the FT of the interferogram. The spectrum contains absorption band for both the compound and background. Then the computer automatically removes the background from the sample spectrum and gives us the spectrum of a sample being analyzed. Okay, so in this way whole process is happening inside the instrument. Okay. Next is sample preparation. So we discussed earlier that how the instrumentation or what is happening inside the instrument, but we have to know how to prepare a sample which we have to be analyzed for in or by using IR. Okay, so if we have a liquid sample, then what we do, let us see this. A drop of a liquid organic compound is placed between a pair of polished sodium chloride or potassium bromide plate, which we referred as a salt plates. When the plates are squeezed gently, a thin liquid layer forms between them. A spectrum determined by this method is referred to as a net spectrum, since no solvent is used. Salt plates break easily and are water soluble. This is the advantage of salt plate. The pair of plate is inserted into a holder that fit into spectrometer. Next is solid sample. What if we have a solid sample to be analyzed on the IR? So there are total 3 methods for preparing a solid sample for IR spectroscopy. The first method is finely ground solid sample with the powdered potassium bromide and pressing the mixture under high pressure. Because of pressure, potassium bromide melt and seal the compound into the matrix. The results in a KBR pellet that can be inserted into a holder in a spectrometer. The main disadvantage of this method is potassium bromide is a water absorbent which may interfere with the spectrum. Okay. If a good pellet is prepared, the spectrum obtained will have no interfering bands because potassium bromide is transparent down to 400 cm inverse. Okay, second method is nozzle mold. Involves grinding the compound with mineral oil nozzle to create a suspension of finely grounded sample dispersed in a mineral oil. The thick suspension is placed between salt plate. The main disadvantage of this method is that the mineral oil obscures bands that may be present in the analyzed compound. Nozzle bands appear at 2924, 1462 and 1377 centimeter inverse. Okay. Then the third common nozzle oil is nothing but we all may hear this name in Marathi. It called as a currants. Currants oil is a nozzle oil. The third common method used with solid is to dissolve the organic compound in a solvent, most commonly carbon tetrachloride. Okay. Again, as was the case with mineral oil, some regions of spectrum are obscured by bands in the solvent. The region around 785 cm is inverse is obscured by the strong CCl stage that occur there, and we get the spectrum of our compound as well as the spectra of CCl4. Now correlation charts and table. We will discuss instrumentation, what is happening inside the instrument, then how to prepare sample for analysis. Now correlation charts and table. So what is correlation charts? Let us see. To extract structural information and infrared spectra, you must be familiar with the frequencies at which various functional groups absorb. You may consult infrared correlation table, which provide us much information as is known about where the various functional groups absorb. The reference listed at the end of this chapter contain extensive series of correlation tables. The absorption information is presented in the form of chart called as correlation chart. So correlation charts or table is nothing but a chart which gives us frequencies at which various functional groups absorb IR radiation. So this is the correlation chart which giving us the types of vibration, frequency, intensity. Okay, so here first is CH, alkane. Alkane stretching frequency is 30,000 3000 to 2850 for and then for alkane it is not interpretatively useful. Okay, let us see about CH stretching. In CH we know that we just discuss about the bending vibrations, in plane bending, out of the plane bending. So you can see here for each and every vibration there is different frequencies. Okay, so this is frequencies for OH, NH, C single bond, N, C double bond, N, that is C triple bond, N nitriles, and so on. So by using this we can interpret the IR spectrum. These are some basic values for absorption of a bond. OH bond is showing frequency at 34,000 centimeter inverse. NH shows 34,000 centimeter inverse. CH shows 3000. Okay, now we have, for example, we have discussed about instrumentation, then sample preparation, and what is correlation chart. Correlation chart gives us or help us to interpret the IR spectrum. Now examination of IR spectrum. What is IR spectrum? The information whatever we have get from the instrument in readable form. Okay, so how what is the definition? Actual proper definition is plot of absorption intensity versus wave number is referred to as an infrared spectrum of the compound. An infrared spectrum determines the positions and relative size of all the absorptions or peak in the infrared region. Okay, I have shown here a infrared spectrum of 2-bromopropane or 2-bromopropane. Okay, as I have told you here, plot of absorption intensity versus wave number is referred as the infrared spectrum of the compound. To absorption wavelength we also called as a to wave number we also called wavelength. Okay, so you can see here we have plotted the plot of wavelength versus wavelength versus absorption. In y-axis there is absorbance and in x-axis there is wavelength. Okay, so in these spectra you will see the CH stretching peak at 2950 centimeter inverse, CH bending peak at 1450 centimeter inverse, and CBR stretch frequency at 640 centimeter inverse. Okay, how we know these values, or how we interpret this IR? We see the structure of the molecule, then we see in a correlation chart CBR stretching is frequency, then we see in this IR spectrum whether this spectrum showing us peak at specific frequency which is mentioned in the correlation table. Is that frequency is mentioned or giving us peak at that specific region or not? If it is giving frequency in that particular region, then we can say that CBR bond is present or CBR is present in that molecule. If not present, then it is not present in that molecule. Okay, these are some references which I have used for preparing this lecture series. I hope you all understand this. Thank you and happy learning.